Okay, 9b, we're focusing on linear modeling. So linear, of course, comes from the word line. So let's talk about, or remind ourselves what a linear function is. So linear function is a straight line with a constant rate of change. That is the main thing you're looking for to determine if it was a linear, right? You have a constant rate. Of course, another word for rate of change is slope. The steepness of your graph. You're always going to read it from left to right, just like we read left to right. So if you're looking at a graph such as this one has a positive slope because from left to right it is going up. To figure out the steepness, you're going to say, okay, how quickly does it rise? So you need to see the change in distance. So in this case, distances are y. We need to change how quickly it goes up for each step to the right. So if we go up 6 and 1 hour over, then we have described the steepness of our graph. And to put that together, we take our change in distance over change in time. So vertical change over horizontal change, so it goes up 6 miles every hour. Okay, note that never mind, I'll come back to that. Okay, so this dotted line triangle is kind of how we're going to do it. So you can either make the triangle above the line or you can do the triangle below the line. Either way, you're always going to have the height divided by the width. And because we do the height first, we talk about that as the rise over the run, obviously. Not obviously, but I'm sure you've heard that before. So the keywords here to try to find that rate, you might see the actual word rate, the rate is. You'll see the word per, or for each, or for every, or they'll actually give you something like miles per hour. Now, if we only have points, right, we want the change in y to get that height, we could take the difference in our two y values, divide by the difference in two x values. And we'll see examples of those as we work through this. Okay, let's consider this graph. So here we have a graph comparing the rain depth in inches to the time in hours. So first, let's describe the function on the graph. So we have 4 choices. Each of them we're talking about how the rain depth and time are connected, how they are related. So the first choice, the rain depth increases by 1 inch every 3 hours. The rain depth increases by 3 inches every 1 hour. The rain depth decreases by 3 inches every 1 hour, or the rain depth decreases by 1 inch every 3 hours. Okay, so reading left to right, we see that the graph is increasing, which means that we know that the rain depth isn't decreasing. So we need to know how much does it increase for every length of time. So when we're looking at rain depth as our y, so we want to see how far up does it go for each step. So the first one increases by 1 inch every 3 hours. That would mean it goes up 1 and over 3, and the point would have to be here. But that's not how it works, right? So we know it's not that one, so it should be this one. So it increases 3, so from 0, so we go up 3 inches every 1 hour. So 1 hour is over here, and we are back on the graph, so that one is correct. Okay, so that's in words. Now let's express this as a slope or rate of change. So the rate of change is going to be increasing and that's going to be the first the y value per the x value. The y value is rain depth, so it's going to increase by 3 inches per hour. Now if we're writing that as a slope, which we usually call M, we'd have 3 inches over 1 hour, or just 3. And because it's increasing, it is a positive. Okay, the last thing, briefly discuss the conditions under which linear function is a realistic model for the given situation. So realistic. So when can we use this model? Well, we can only use this model if it's actually linear, right? And the big thing about linear function is that it has a constant rate of change. So when you're looking at the answers here, you're looking for that word constant. Now, all these have the word constant, but the second one says it's not constant. Third one says it's only constant for 2 hours and then changing for 2 hours. Last one says it's changing and then constant. Well, the only time we can actually use a linear function is if it always remains constant. So that would be answer A. It's a different one. Okay, so this one, we see it's going down from left to right, so this one is decreasing. So we first talk about our y values and how that correlates with our x values. So we first talk about how our y's change. So our y's are decreasing, right, as we go from left to right. So we know it's not going to be B or D. So how much is it decrease? So we have either decreases by 6 miles every 700 hours, or we have decreases by 700 miles every 6 hours. Well, 6 miles would just be, right there. And then 700 hours would be way over to the right. So that one, it's definitely not it. So if we're looking at how much we decrease, we kind of want to find 2 points where it crosses the crosshairs here. And really the only place we see here is at the very beginning and the very end. So we want to say, okay, how far do I have to go to get from one point to the other? And the great thing about linear is that it really doesn't matter which 2 points you choose, because it's going to be the same slope no matter what, right? Because it's constant. So we can always go from the beginning to the end. So from the beginning, we have to get all the way back down to the x-axis. So we have to go this whole entire length, which is 700. And then we have to go this entire length down here, which is 6 hours. So it decreases 700 every 6 hours. So expressing this as a rate of change. So in this time, it is decreasing 700 miles per 6 hours. As a slope, though, we don't want to get rid of all the words. We just want the number so that we can put it in an equation. So the decreasing means it's going to be negative. 700 miles is our rise, and 6 hours is our run. So then we do negative 700 divided by 6, and we get a negative 116.6 repeated. And that would be our slope for this one. Okay, part C, same thing as the last one. The conditions under which a linear function is realistic. Again, you're looking for that is constant for the entire time. So again, it is A. Example 3, the following situation involves a rate of change that is constant. Write a statement that describes how one variable changes with respect to the other. Give the rate of change numerically with units and use the rate of change rule to answer any questions. Okay, so the water depth in a lake decreases at a rate of 2 inches per day because of evaporation. How much does the water depth change in 8 days and then in 15 days? Okay, so first we need to figure out what is our independent variable and what's our dependent variable. And so we have to figure out the 2 things that we are comparing. Well, we can see that we're looking at the water depth in a lake. That one is a lot easier to see. Now the other one is a little bit trickier because it doesn't actually really tell us what's going on. So in that case, we can look at the rate. So we have a rate of 2 inches per day, and that rate can help us figure out what the other variable is. So we can go ahead and answer B a little bit. So we have the rate is 2 inches per day, and we are decreasing. So we can fill in this part here. So we're decreasing 2 inches per day. Okay, so we know that the rate always talks about the y values here and the x values here, our vertical and our horizontal. And we know that our x is our domain, so that is going to be our independent variable, and y is going to be our dependent variable. So from here we can get a little bit of a clue on what we're talking about. So when we're looking at, we know one thing we're talking about is water depth. Well, the only thing, out of the units here of inches and day, one thing that we'll talk about water depth is the inches. So you know that the water depth is going to be my dependent. And we just have to figure out what my independent is. Well, the independent is measured in days. And well, what do we measure in days? We measure time. Specifically, it's going to be the amount of time from when you first started measuring. So the independent is time and dependent is water depth. Okay, so we have this word varies with respect to. So that's another way of saying as. And we talked about in 9a that what comes after as is the independent. So we're going to put the independent here. So we say water depth varies with respect to time with a rate of change of, actually decreasing doesn't really make sense here in English, right? So instead of saying decreasing, we are just going to put a negative. And saying that makes a little more sense with a rate of change of negative 2 inches per day. Okay, so now that we've got that, we can then answer questions about this rate. So how much does the water depth change in 8 days? Well, we know that every 1 day it changes by a -2. So we can either add the -2 8 times, right? We have a -2 for 1 day, -2 for another day, -2 for a third day, fourth day, and so on, right? Or when we do multiple additions or subtractions, the same thing as multiplication, right? So we have a -2 added 8 times to get a -16. Now note, if we look at the units, right, because this is a real world problem, we always have units, we can see that we also need to multiply here because we have a -2 inches per day, right? If we multiply that by 8 days, days cancel and you're left with just inches, which is what I want, right? So I want to know how much does the water depth change. So I want to know an amount of inches. So it changes -16 inches. Right, because it says change here, we are going to include that negative. Okay, so now how much does the water depth change in 15 days? So the same thing, we can either add the -2 15 times, which is just a little crazy, or we can multiply it by 15 to get a -30. So it changes -30 inches. Again, looking at the units, you would have -2 inches per day times 15 days. Days cancel, and you are left with a -30 inches. Another situation. Okay, so this one again is constant. We have a driverless car maintains a constant speed of 63 miles per hour along a highway. How far does this car travel in 1.5 hours and then in 3.8 hours? Okay, so again, we're trying to figure out what variables we're talking about and what that rate of change is. So here we see the word per, and that tells us that we're looking at the rate. So we have speed of 63 miles per hour along a highway. So in this case, because we're not saying we're like going in reverse, we're just going forward, the rate of change is going to be a positive 63 miles per hour. And we're going to use that to help us figure out what our variables are. So our dependent is on top because that's my y's, and independent on the bottom. So our dependent is miles. Well, we're driving along, so if we're going to measure something in miles, that's going to be your distance. So my dependent is going to be the distance that I've traveled. My independent is hours. So again, if you're driving along, you can measure distance and you can measure how long you've been doing it. Again, my independent variable is time. So with respect to is the same thing as. So my independent goes there, and my dependent goes first. So my distance traveled varies with respect to time with a rate of change of a positive 63 miles per hour. Okay, now again, we want to find the distance traveled after 1.5 hours. Now this one, it would be a little bit hard to do just by adding, right? You have 63 plus whatever half of that would be, right? So instead of trying to do all that, remember multiple addition, same thing as multiplication. So we can just do 63 times 1.5. And we get 94.5 miles. Okay, same thing here. If we want to travel after 3.8 miles, again, that would be even harder to add up to figure out what that 0.8 would be. So we do 63 times 3.8, because that's how many times we want to add it. Multiply that together, and we get 239.4 miles. So bonus question. So this is how much it's changed, right? This is how much I've traveled from the first that I started measuring to the second part. Well, what if we started the speed 15 miles from home? Because of course you can't just jump up to 63, right? So let's say it took us 15 miles to get up to that speed. Now how far away from home are you after 3.8 miles? Well, when we started 63, I was 15 miles per home. And then at 63 miles per hour, I traveled this 239.4 miles. So if I add that on, that would tell me how far I've traveled total, right? So that would be 254.4 miles. And that, in essence, is all we're doing for linear equations, linear modeling. We are taking where we start and then how much we've changed. So I'm sure you've seen it as y equals mx plus b for a linear equation. Well, I'm going to look at it a little bit differently. Because these two are added together, we can add them in any order. So let's say we have y equals b plus mx. And of course, our slope could be negative, which is why we have that negative here. So our y values are going to be your dependent variable. And in the function, it's like to get the actual function, it's going to be a variable. So usually you leave this as a variable unless you are trying to answer questions about it. Your b is your beginning. So where you start. So like in this bonus question, it would be that 15 because that's how far you started from home when you got to that that speed. So this is your beginning value. M is how much you've moved. This is your slope. Well, it's not how much you moved, it's the way you move, how fast you move. So that's your rate. And then x is going to be your independent variable. So when you're writing out an equation, an actual function, you're going to keep the y and the x in there, and you're going to replace b and m with numbers. So let's look at some examples. So example 5, the following situation can be modeled by a linear function. Write an equation for the linear function and use it to answer the given question. So the price of a particular model of car is $18,000 today and rises with time at a constant rate of $900 per year. So remember, this constant rate, it confirms that it is linear. How much will a new car of this model cost in 3.5 years? Okay, so to answer the second one, let's create a model that describes this. So first we need to know what is our dependent and independent variables. So we're looking at a price of a car and it rises with time. So this says time and price are the two things we're comparing. And because the price rises with time, that means time is the thing that causes it. So that is my independent and price is my dependent. And we can confirm that looking at the rate. So it's $900 per year. So dependent is always on top, and so we have dollars on top and time on the bottom. So my time is measured in years and my price is measured in dollars. So then we need to know what my B and my M is. So my B is my beginning value. Well, the price starts at $18,000. So today it's at $18,000. And my movement, so how this is going to move is it's going to rise $900 per year. So because it's rising, it's going to be a positive $900 per year. Putting it into my equation, I would have y equals 18,000 plus 900x. So we start at 18,000, and then for each year I add $900. Now, this mentions that we want to use P for the price of the car and T as time in years. So while this is the general, if we want to change the letters so it makes it a little bit more, not personalized, but a little bit more relevant, so we can remember which one's which, we can change, because Y was my price, I can change that to P, and then I change X to T. So my price is 18,000 plus 900 times T, which is the number of years. Okay, now I can use this equation to figure out the price of the car after 3.5 years. So before, what we would have done is we would have taken 3.5 years, multiply it by our rate to figure out how much it changed, and then add it back on to what it was originally. Well, we're still going to do that. We're just going to do it all at once. So they want the price of the car, so we're going to leave P. They give us a value of years, so that is going to be my value of T. So I'm going to put 18,000 plus 900 times 3.5. So I can put all that in my calculator, and I would get 21,150. So the price in 3.5 years would be $21,000 and $21,150. Example 6. A snowplow has a maximum speed of 40 miles per hour on a dry highway. Its maximum speed decreases by 1.1 miles per hour for every inch of snow on the highway. According to this model, at what snow depth will the plow be unable to move? Okay, so this one's a little bit trickier because we have a lot of pers in here. So we have 40 miles per hour, then we have it decreases by 1.1 miles per hour for every inch of snow on the highway. Okay, so to get the rate, right, you need some word that indicates change along with the per. So we find the pers, but the only ones that actually have a change associated with it is this 1.1 miles per hour for every inch of snow, and that says decreases. Okay, so my rate is going to be a decreasing 1.1 miles per hour. Then we have again for every, so that's another per inch of snow. So in this case, we are comparing speed with the amount of snow. Okay, so because speed is on top, this is going to be my dependent, and the amount of snow is going to be my independent. And they want us to use S for the speed of the snowplow and D for the snow depth. So we're going to have S equals something, my rate is negative, and so M, actually let's back up a little bit. Woo, not that far. Okay. So I know I'm going to use S and D, but I still need my B and my M. So B is going to be where we start at. So reading back through it, so we have snowplows maximum speed of 40 miles per hour on a dry highway. A dry highway, that means the snow depth is 0, right? So that would be our starting point. So my B is going to be 40 miles per hour. And my rate here is what I just looked at here, so 1.1 miles per hour for every inch of snow. So because it's decreasing, it's a negative 1.1 divided by 1, so it's a negative 1.1 here for M. Plugging it in my equation, I have my speed is going to equal my starting speed minus 1.1 for every inch of snow. And that goes there. Okay, now we can use this equation to help us answer this next question. So the snowplow will be unable to move when the snow is how many inches deep? Okay, so it doesn't actually give us a number here, but it does say unable to move. Well, it's unable to move, that means the speed is 0. The maximum speed, so it can't go at all, so its speed would be 0. So it wants to know number of inches, that is my depth. So it doesn't know my depth, I do know my speed, so I'm going to put this value into my equation. So instead of S, I'm going to put 0 equals 40 minus 1.1d, and I'm going to solve for d. So to get d by itself, I need to get rid of the 40, so I'm going to subtract 40 from both sides. So I have a negative 40 equals a negative 1.1d, so I need to divide both sides by negative 1.1, and I get a d of 36. So the snow will be unable to move if the snow is 36 inches deep, which we can say from Model 1 that is 3 feet. So if it's 3 feet deep, the snowplow would not be able to move in it. Okay, example 7. Again, we can model the situation with the linear function. You can rent time on computers at the local coffee center for $10 setup charge, an additional $2 for every 5 minutes. How much time can you rent it for $25? Okay, so independent variable is going to be either rental cost or time, and the dependent variable is going to be the other one. So again, you can think of it logically, which one depends on the other. You can also look at the rate they give you to help you figure that out. So if you're looking for the the keywords here, so we have an additional, which is our change word, and then we have for every. So we are increasing $2 for every, right, is another word saying per 5 minutes. So our dependent is on top. So our dependent would be my dollars, which is my rental cost, and my independent is time. So to get the linear model, we need our B and we need our M. So my B is that where we start with. So when we run a computer, there are fees, right? So we say we can rent time for a $10 setup charge. So that is what you're going to pay regardless. So you're going to start with this $10 setup charge, and then you're going to add on $2 for every 5 minutes. So it's going to be positive because you're adding it on. So it's $2 every 5 minutes. So you can leave that as a fraction, or you can change it to a decimal. Okay, so linear models this function or situation. So we have our dependent, which is r, equals my b plus my slope times my independent. So my rental cost is 10 plus 0.4 t, where t is time in minutes and r is in dollars. So how many minutes can be rented for $25? Round to the nearest minute as needed. Okay, so we want to know how many minutes. So how many minutes is our t? That's what we don't know. They give us $25, so that is my r. So I plug in 25 for r and solve for t. So I subtract 10 from both sides, divide both sides by 0.4, and I get 37.5. Now rounding this, because this says round to the nearest minute, but that would be 38 minutes. Now, of course, 38 minutes is actually going to be a little bit more than 25, right? Because we rounded up. Realistically, you would have rounded down so that you can ensure it is less than $25. That's not what it told us to do, so telling us what to do, it's just 38. Okay, so is a linear model reasonable for the situation? So in general, do you have a constant rate of change? Well, in this case, it says it's just $2 every 5 minutes, so you could say that it is. However, notice that it says every 5 minutes. So because it says every, this is actually going to be like a step function, meaning, so it's going to be $10, right? So like for the first 5 minutes, and then it's going to be $12 for the next 5 minutes, and then it's going to be $14 for the next 5 minutes, and $16 for the next, and so on, right? So it's not actually linear, but you can still use this for like some estimation purposes. It's just not going to be exactly accurate. I mean, you can kind of make it more accurate if instead of t being the number of minutes, the number of 5-minute increments, but that just makes things a little bit more complicated. Okay, example 8. Campus Republicans fundraiser offers raffle tickets for $10 each. The prize for the raffle is a $350 television set, which must be purchased with the proceeds from the ticket sales. Find a function that gives the profit or loss for the raffle as it varies with the number of tickets sold, and how many tickets must be sold for the raffle sales to equal the cost of the prize. Whew, okay, so to get the equation of this, it tells us that P is the profit in dollars and T is the number of tickets sold. So which one is independent, which one's not? So looking at the information they give us, so we sell raffle tickets for $10 each. There's another way of saying it's $10 for each ticket, right? So that is going to be my M. So it's $10 for each ticket. And of course, you're adding money as you sell stuff. So that's going to be a positive 10 for my slope. The prize for a raffle is $350 television set, which must be purchased with the proceeds from the ticket. Okay, so if we're thinking about so independent and dependent. So we have the dependent on top, which is money. So the profit is going to be my dependent, and number of tickets is going to be my independent. So it's going to end up being a P equals. Okay, now profit. Profit comes from, it's going to be all the money you get in minus all the money you get out. So at the very beginning, you haven't made any money, right? But you do know that at some point you're going to have to purchase this $350 television set. That is your money out. So initially, you start with zero money in, and you lose that $350. So the initial profit is actually going to be a negative $350. So that is your B. And then you're going to add on the $10 per ticket. So $10 per ticket times the number of tickets. Okay, part B, ticket. How many tickets must be sold for the raffle sales to equal the cost of the prize? Well, the raffle sales to equal the cost of the prize. Now we can use our equation here. If we say if the sales are equal the cost, that means my in and my out is the same, which means my profit is 0. So I'd have 0 equals negative 350 plus 10t. Add 350 to both sides to get that. Now pausing here, if you didn't want to think about in the profit, you could logically say the raffle sales is going to be $10 times the number of tickets, and it's going to equal the cost of the prize, which is $350. So you could, logically start here if you wanted to. But if you didn't see that, that's okay. If we're just looking for the profit and time or tickets, it tells you the profit here. So continuing on, so we divide both sides by t, and we get that t, or by 10, and we get that t equals 35. So you'd have to sell 35 tickets in order for the raffle sales to equal the cost of the prize. Example 9, a $1,500 washing machine and a laundromat is depreciated for tax purposes at a rate of $125 per year. Find a function for the depreciated value of the washing machine as it varies with time. When does the depreciated value reach 0? So here it tells us that the depreciated value varies with time, which tells you that time is your independent and the value is your dependent. And we see in our directions here that we want to use t and v as our variables. So of course t would be time and v would be your value. So we need to know what our b and our m is. So we know that our dependent is this value. So we need an initial value or a beginning value. And we see that it starts at $1,500. So there's a $1,500 washing machine that then is depreciated. So 1,500 is our initial, and our slope, we see that's depreciated for tax purposes at a rate of 125 per year. So my slope would be negative because it's depreciating $125 per year. And per year is a 1, so it's just divided by 1, which is the same thing. So to put it in my equation, I know my value is going to start at 1,500, and it's going to decrease 125 per year times t years. So how many years does it take for this machine to depreciate to $0? So the value then would be 0, and it wants to know t, the number of years. So I put in 0 for v, So I have 0 equals 1500 minus 125t. Subtract 1500 from both sides. Divide both sides by negative 125. And I get that t is equal to 12. So it would take 12 years this machine to depreciate to $0. Okay, so the general formula for linear function. So it doesn't mention on here, but one thing you always need to know is what are your variables. You need to know what is your independent variable, what's your dependent variable. That way you can put them in the function the right way. So far they've always given us the rate, so we can use that to help us figure out what the dependent and independent are. But if they don't give you the rate, you are probably going to have to figure that out yourself. So once you do define the variables, you can find 2 data points. Using the 2 data points, you can find the slope. Then you can find the y-intercept, the beginning. Sometimes it's given to you. If it's not, then you can find it using one of your data points, your slope, and the general equation to solve for b. Once you have b and m, then you can write your equation in y equals mx plus b or y equals b plus mx form. Okay, so example 10. Suppose your pet dog weighed 5.5 pounds at birth and weighed 20 pounds a year later. Based on these 2 data points, find a linear function that describes how weight varies with age. Use this function to predict your dog's weight at 5 and 10 years of age. Okay, so it tells us to describe how weight varies with age. So that tells us that age is going to be my independent and weight is going to be my dependent. So again, you always need to know what you're solving for. And when you're putting it into points, you always put the independent first because that is your x. So it doesn't tell us what our slope is. We're going to have to figure that out based on a couple things that happen. So we look and see the relationship. We need to find 2 relationships between weight and age. Well, we know that it weighed 5.5 pounds at birth. Well, at birth, your age is 0, and they want us to use W for weight, W for weight and T for years. So at birth, the number of years would be 0, and your weight is 5.5. And then we see that it weighed 20 pounds a year later. So in this case, the T would be 1, and your weight is 20. So our 2 points here is we put our independent first, which is our age. So we have to put 0 and 5.5 and 1 and 20. So using those 2 points, I can figure out the slope. So we need to know how much it rose and how much the weight rose. So we have gone from 5.5 to 20. So we generally take the ending amount minus the beginning amount. So my y2 minus my y1. And divide by how far we've gone left or how far we've gone right. So again, we take the second one minus the first one. So my slope would be 14.5. So we're saying that our weight is increasing by 14.5 pounds per year. So my starting amount. Now in this case, it actually gives it to you because it says it has your starting amount at birth, right? It's 5.5. But let's say it didn't give it to us. So we have to figure out what that would be. So let's just take this point. Now, it doesn't really matter which point you choose. This one, the first one would be easier, but just for illustration purposes, I'm going to use the second one. So if we're going to figure out our b, we plug this point and our slope into the equation as we know it. So normally it would be this, right? So the weight is going to be my initial plus my slope times my t. So I'm going to plug in what I know. So I know that at 20 pounds, it was my initial, which I am assuming I don't know at the moment. And I've increased my 14.5 pounds, and I've done that for 1 year. So I plug in 20 for W and 1 for T, and now I'm going to solve for B. So 20 is equal to B plus 14.5. Subtracting 14.5 from both, I get 5.5. So now I have my B, I have my M, so I know my W is going to be equal to 5.5 plus 14.5 T. So according to this model, the weight of the dog after 5 years, so my T is 5, and I want to know my W. So my weight is going to be 5.5 plus 14.5 times 5 years, which is 78. So according to this model, after 5 years, my dog would weigh 78 pounds, which is actually possible for some dogs. But how much would this model say that the dog weighs after 10 years? So this time our T is going to be 10. We want to find our W. So W is going to be equal to 5.5 plus 14.5 times 10, which is 150.5 pounds. Which again might be possible, but that's pretty dang heavy for a dog. Now, what statement best describes the validity of this model? So can we actually use a linear model to describe the situation? So choice A, the model is only accurate for large ages because when the dog is young, it grows faster than when it's older. B, the model is never accurate because the dog's weight and age are not related. C, the model is only accurate for small ages because the dog will eventually stop growing. Or D, the model is always accurate because the dog will continue to grow as it gets older. Well, anyone who knows animals knows that everything stops growing at some point. We also know that age and weight are related in some ways, so we know it's not B. So is it only accurate for large ages or for small ages? Well, the only one that really makes sense is this first one, because the dog eventually stops growing, right? They don't grow slowly at first and then increase until they're dead. So we know it's not A, and it has to be C. And that is it for 9B.